Okay, well, I am doing what I said I was going to do a couple of videos. It is 4:10 p.m. I still have coffee from lunch. Iced coffee at this point. Anyway, I have the whole thing on the board here for you. Let me walk you through the explanation of number 38 to start with. It says an open tube, U-tube, of mercury. So the pink is mercury. It has some mercury in the bottom, and it is displaced by water. It says what column of height would displace the mercury 4 centimeters on one end. So water coming in the side displaces it up 4 centimeters. How much water would it take to do that? And 13.6 grams per cubic centimeter is the density of mercury. It's right there in the question. And then, so what's the density of water? 1 gram per cubic centimeter. So how much would it take to push that up that amount? You take your 4 centimeters times 13.6, because that's how much more dense mercury is, and you'll get how much water, height of water, you would need to do it. 54.4 centimeters of water. If you have any questions, let me know. Okay, I told you I would take my time on this one. This one, full disclosure, this gave me an almost headache, okay? And it's a lot later. It took me a while to get it all to the point where it's easy-ish to understand. So, A, pressure at depth, 43A. It says a bathscaff, bathscaff? I don't even know what that is. Some sort of device that goes to a depth. Descends to 11,000 meters in the Mariana Trench. What's the pressure at that depth? So we have some known things we can find in the textbook. That's salt water. We're going to approximate it. Okay, this little swoopty equal sign means approximately 10,000 newtons per cubic meter. Awesome. Depth is given to us in the question, 11,000 meters. The formula to find pressure at depth is weight density, which is right here, times the depth, which is right here. So we plug it in, and we get 110 million pascals. If you thought that was too big to be true, you're wrong. It's correct. And then best practice for a number that large, throw a K before the pascals and make it 110,000 kilopascals. Done for part A. Part B, okay, we've got the pressure at that depth. Now we want to know how much force is being applied over a certain round area. So the question says, how much force on an observation glass with a diameter of 16 centimeters? We've got to find the area. So dust off your circle math from whatever year you learned that for the first time. And we've got area is equal to pi r squared. So we're not given a radius, but I think we can figure out what half of 16 is. And we get area is equal to 3.14 times 64 square centimeters. Awesome. What is that? 201 square centimeters. That is the actual area. Awesome. We're not done yet. Now we got to go over and figure, okay, so force applied to that area now. All right. To make things the simplest, I went back to our 110 million pascals. So we didn't have to divide and then multiply back and forth by 1,000, okay? So we have 110 million pascals. And a reminder here, a pascal is a newton per square meter. Well, our area is in square centimeters. So we're going to divide by 100 to get our amount of newtons per centimeter squared, okay? So it's a 1.1 million newtons of force for every little square centimeter, okay? And we said we have 201 square centimeters, so we just multiply, and you get these big numbers. I got this gigantic number. I'm like, there's no way. Well, remember, a pascal is kind of a small unit, okay? So 223,333,331 newtons of force applied to that small viewing window. That's scary stuff. That's scary amount of force. Now, Remember, this is rounded, so when I double checked, double, triple, however many checks I was on to make sure my math was right, because I never trust my math. So I always multiple checks. It's a little off from what the real physicists in college and whatnot are putting out. Now they did it in atmospheres. I think his last name was Anderson. I was watching his. He did it in atmospheres. It's 1,000 atmospheres. So what I did to check it is I said, okay, if the depth there is 1,000 atmospheres, how many pascals for one atmosphere? And then I worked my math back from there, and it worked out to like just over 200 million newtons of force. So we aren't off by much, and we know we have rounding error here because we just said to make math simple, we'll say 10,000 newtons per cubic meter of water. For salt water, that's close. Okay, the real number I think is in the textbook. All right, so that's part A and B. Part C, you're going to use the same techniques from A and B to get the force applied to the diver's 16 centimeter, conveniently the same size, faceplate or whatever, at 20 meters depth instead of 11,000 meters depth. And then you can compare. If this isn't way more, you did something wrong. Your force at 20 meters depth should be a lot less for number 42. So that's part C's to compare. Whew, that was tough. Number 48, A, B, and C. Here we go. We've got a crown. So it says a king's crown presumed to be, so thought to be, we're told it is pure gold, has a mass of 1 kilogram. When submerged in water, its apparent mass is measured to be 0.92 kilograms. Well, how do you get apparent mass? Well, you see how much the water displaces weighs, whatever. It's getting late. So A says, what is the buoyant force in newtons? So buoyant force in newtons, apparent mass is 0.92 kilograms. Newtons, remember, is mass times acceleration. So we have 0.92 kilograms times 9.8 meters per second squared, which is acceleration due to gravity here on Earth, where we live. And you just multiply it, and you get 9 newtons of force. So buoyant force is 9 newtons. Awesome. Part B. What volume of water in liters is displaced? Well, it tells us the apparent mass is 0.92 kilograms. And we know that water is 1 gram per milliliter, which is the same as saying 1 kilogram per liter, right? Because we're just jumping up times 3 on the units there. So you got to know metric math a little bit, right? Or you could have converted down to grams. It works either way. But so if we have 0.92 kilograms, we know it should be the same number. 1 equals 1. 0.92 should equal 0.92. So volume would be 0.92 liters as the volume of the water displaced. Finally, C, it says, is the crown made of pure gold? And then it gives us the actual known density of gold at 19.33 kilograms per liter. Well, it told us it's a 1 kilogram crown. And we know the volume of water that was displaced, right? So you're telling me that 1 kilogram per 0.92 liters is the same as 19.3 kilograms per liter? 1 liter isn't far from 0.92, is it? So this number should be way higher. It'd probably be somewhere in the 18s, I guess, right? Something like that. 17, 18 kilograms would have been the weight of that crown had it actually been made of pure gold. This is barely more dense than water. I mean, good grief. This is really light. It should be way heavier. So gold, no, it's not gold. It is not equal to, right? So no, this is not gold. Moving on. Number 49 on chapter 19. Moving actually along pretty quickly now. Number 43 was a bear. So we've got a cross-sectional area of an output piston in a hydraulic device is 10 times the output pistons, or excuse me, 10 times the input pistons area. So A is by how much will the device multiply the input force? So you've got an input area times 10 equals the output area of these pistons, okay? So the output force will be 10 times the input force. And then it says, okay, how far will the output piston move? Well, it's going to move one. It doesn't give us numbers to work with. It's just a comparison. So it would be, since it's 10 times the area, it'd be the inverse of it, right? It'd be the opposite of it. So it'd be 1/10 the distance. So if you move, so to confirm, we'd say if you, let's say the force was 1 Newton, and it moved 10, whatever it is, 10 centimeters or whatever, then the opposite of that would be, the force would be 10 times as much, right? So is what we said here. And then the distance would be 1/10, which would be 1. Instead of, 10 centimeters, it'd be just 1 centimeter, right? So shorter distance. Is that true? Is 1 times 10 the same as 10 times 1? Yes, it is. It works. No, we were confirming here the conservation of energy. We did not create or destroy energy with that. Okay, good for number 49. Okay, number 50, medium difficulty level, I would say, medium to hard. Suppose the piston in the hydraulic lift of figure 19.2, which is 2 pages prior to the question, has a cross-sectional area of 0.1 square meters. A, what air pressure must be produced by the air compressor to support 10,000 newtons, which is the combined weight of the car and the lift? Okay, so we've got 10,000 newtons. Remember, a newton is a kilogram meter per second squared. And we're given our output piston area of 0.1 meter squared. So we're going to divide out to get, what are we looking for? We're looking for how much, how much air pressure is needed. Well, looking for how much force. Force includes kilograms, right? So, and we're looking for pressure, and we're used to using pascals and kilopascals. So we need the kilograms, right? So we're going to divide out the 0.1 meter squared so that we can get rid of the meter per second squared too, because we don't care about the time factor. We're just supporting the weight indefinitely, right? So that gives us an answer of 100,000 kilograms. The newtons are gone because that's part meters per second squared. You got meters squared. All right, so let's get rid of it. And then we would generally use kilopascals because that's a big number. So we'll divide by 1,000 to get 100 kilopascals. Okay, so 100 kilopascals. How did I jump to that? Because I feel like I just jumped to that. I didn't. I did a little bit of work, all right? I checked things out to make sure everything made sense. So think about it for a second. What is a Pascal? We wanted 100,000. If they're pascals, they're actually, isn't it actually 100,000 Newton divided by meter squared? Yes. Aren't newtons kilogram meters per second squared? Yes. So I'm like just showing you how I got there, okay? So if you got 100,000 kilogram meters per second squared divided by a meter squared, we can get back all the way to pascals. So they can be used interchangeably is what I'm trying to get at. 100 kilopascals would be the equivalent weight support of 100,000 kilograms. I'm like, wait a minute, 100 kilopascals, isn't that about 1 atmosphere? So I checked, and surely 100 kilopascals is equal to not just 1 atmosphere, but also 14.5 approximately pounds per square inch, which is atmospheric pressure. So they're all the same. What are they actually getting to here about the question? We're holding a lift up. As long as you have at least 1 atmospheres of pressure, 14.5-ish pounds per square inch, 100 kilopascals in the system. It's just supporting the weight. It's not lifting the weight. It just has to hold it. Okay? If the air compressor was disconnected and all the pressure left, that car would come down and push all that air out. Eventually, the air would balance out, and you still have 1 atmosphere of pressure left in the reservoir. It just has to hold it. So the air compressor can just kick on to maintain that pressure. If there's a leak in the system, it just have to kick on every once in a while, but it's just got to sit there off. As long as no air is escaping, that air compressor just needs to hold it at 1 atmosphere of pressure, which is 100 kilopascals. It all gets back to remembering that a Newton is a kilogram meter per second squared, and that a Pascal is a Newton divided by a meter squared. It's a definitions question. Okay, so if I haven't confused you enough there, let's see, this should be easier. Part B says, how far will the output, oh, wrong question. It says, how does this pressure compare with normal atmospheric pressure? I did that part. I already did part B. All right, that's why I was complicated. I was doing A and B together. Okay, and then part C, why is the area of the liquid surface in the reservoir irrelevant, but the cross-section area of the piston is very relevant? Okay, this is the output. This is where the pressure is, final destination of the pressure being put to work. Okay, the pressure is going to be the same on the input side and the output side. The pressure is the same on the input side and output side in square whatever unit you're using. In this case, they're using meters. So the pressure is going to be the same, okay, per square meter. Size of the output area is versus the input area is irrelevant. So put it another way. Let's say we knew the input area. You'd have to go from the pressure to the input area to see how much force is applied on the input side. And then you'd have to convert it to the output side by doing more math. You could just bypass it entirely because it's the same pressure per area. So it doesn't matter what the area is on the input versus output. Doesn't matter. Just skip it. You're doing more work than you have to. Yeah, if that makes sense. I hope that makes sense. I can't explain it any other way right now at this late at night. I don't want to tell you how long it is, Ben. For those of you that, if anybody got all these and didn't take a long time to do it, congratulations, you're smarter than me. It's taken me a while. So, and for those of you that it took the same amount of time as me, good on you for sticking with it. I tell you what, if you did all this work, even if it took as long as me or longer and you got through it, you are a worker. Congratulations. And if you're smarter than me, it's not a competition. You win. If it is, and that's fine. That's a good thing. All right. That's it for chapter 19, requested questions. Holy mackerel. I think that's enough for now. There's only there's only 2. See if they're quick ones. All right, we are on chapter 20, number 39. It says an automobile is supported by 4 tires inflated to a gauge pressure of 180 kilopascals. The area of contact of each of the tires, ignoring the effects of tread thickness, is 190 centimeters. Yeah, still getting confused. 190 square centimeters, which means the total area of the tire contact is 0.076 square meters. Find the mass of the car in kilograms. Okay, they give you more information than you need. All right, they already simplify it. Forget about how many square centimeters. They've already given you the total tire contact area of 0.076 square meters, which is great because pascals are in square meters, so we don't have to convert. fantastic. Notice I started putting information up here like it doesn't matter that there's 4 tires. It doesn't matter how many pounds each. It's that, okay, we've got this much pressure, okay, exerted over a total area right here. That's it. That's all you got to do. So you're going to take your kilopascals. I go ahead and convert to pascals. So 180,000 pascals. What does that mean definition-wise? A pascal is a newton divided by a square meter. Okay? So I've got 180,000 newtons divided by square meters. Times, so that much pressure times 0.076 meters, square meters, gives us 13,680 newtons. But the question wanted the mass of the car in kilograms, the mass, not the weight. Newtons is a unit of force or weight. So we take, remember the definition again, a newton is a kilogram meter per second squared. We're going to divide out the acceleration portion of it to get us back to just kilograms. Well, acceleration due to Earth's gravity is 9.8 meters per second squared, so you divide out the numbers, but you also get rid of the meters per second squared, top and bottom, leaving just the kilograms. Do the math, 1,396 kilograms is the mass of the car. Phew! One more. Can I go home tonight? And finally, we have chapter 20, number 41. The density of liquid air at standard temperature and pressure is about 900 kilograms per cubic meter. What will be the volume of 1 cubic meter of liquid air when it turns into gaseous form? So we've got compressed air to the point that it's not a liquid. So I put it, or not it's not gas. So I put air in quotes because we think of air as being gaseous. So we have a cubic meter of liquefied air. It's compressed, except less space. When it returns to gaseous form, what volume will it take up? And we can think, okay, it's been reduced, it's been liquefied, it should take up more space. So that's the first thing you should be thinking. And then we got to, like, what are we given? All right, the givens are the density as it's liquefied. So the current state, its density is 900 kilograms of this stuff per cubic meter. It's in 1 cubic meter, it says. In the passage, in the chapter, we're also told, we can look up, that standard temperature is 0 Celsius, and the density at that pressure, our density would be 1.29 kilograms per cubic meter. So much less air per that volume of space. So what you're going to do to find the answer is you're going to take your 900 kilograms of air and divide it by how much air there should be per cubic meter. So because you have kilograms top and bottom, those go away, leaving you with just the volume, which is what you're looking for. So that's good. So that's part of the reason why you know you're going to divide that way too. So 900 kilograms per meter becomes 697 cubic meters with just 1.29 kilograms each of those. And you can check your math, right? You can check your math by multiplying this back, and you'll get to that again. You'll get back to the same amount of air. I don't need to use the calculator. I already did. You can, though. So the answer is going to be almost 700 cubic meters of volume that liquefied air takes up once it's released, or once it's allowed to go back to be real air in the gaseous form. Wow. It's been a late night. See you tomorrow. Or wait, that'd be today, or whenever you watch this. Or you might watch this in the future from when you see me. So I'll see you before you watch this. There you go.